Hi, my name is Jamie Gould. I'm a PhD student in the computer science department at the University of New Mexico and a research assistant at Dr. Leah Beakley's lab. And today I'm going to be presenting Travel Slicer, continuous extrusion toolpaths for 3D printing, written by myself and my co-authors, Camila Friedman-Gerlichs and Dr. Leah Beakley. In the traditional 3D printing workflow, you begin with a 3D model that you pass to a slicing software. And in general, in this presentation, when referring to traditional slicing software, I'll be referring to a commercial slicer known as Cura. Cura generates a toolpath in the form of a G-code file, and that is then uploaded to a printer in order to create your 3D print. In traditional slicing software, models are printed layer by layer in a linear positive Z direction. Everything within a layer is printed before the print head moves up to the next layer. And there are two types of movements that the printer makes. Extrude movements, in which the printer is depositing material to build up your model, and travel movements, in which the print head is moving from one area to a model to another. And it's important to note that no material is supposed to be extruding during the travel movements. However, with certain materials, this is not always the case. Direct write 3D printers that extrude paste-like materials, such as clay, cannot always stop extrusion either due to the printer itself or the properties of the material. We developed a novel bronze paste in our lab called Cerametal that can be printed on a direct write 3D printer and then fired in a kiln. However, Cerametal is very delicate and brittle before it's fired, making post-processing removal of the amount of excessive material impossible without breaking the model. Traditional slicers limit the range of printable geometries in these continuously extruding materials because these software was written for printers and materials that can easily start and stop extruding. We developed Travel Slicer to allow us to print more complex geometries and materials that continuously extrude, which it does by reducing the number of travel movements in the toolpath. Travel Slicer breaks the problem of travel reduction into two loosely connected problem spaces: outer model travel, or travel movements that occur between two isolated closed regions, and inner model travel, or travel movements that occur within a closed region during printing, such as between areas of infill and the walls of the print. Travel Slicer takes all the parameters that a traditional slicer does, in addition to two new parameters that correspond to the dimensions of the nozzle height and the maximum nozzle width. Travel Slicer leverages the smaller dimensions in the nozzle with respect to the print head to print in a non-planar order. And it's worth mentioning that in direct write 3D printers, the nozzle is typically much larger than on a fused filament fabrication printer. It then passes these parameters and the model to the algorithm where, like a traditional slicer, it first slices the model into layers. And at this point, we diverge from a traditional slicer by generating a non-planar printable ordering of these isolated regions in outer model travel reduction. And once we have an order, we pass these isolated regions to inner model travel reduction to generate a space-filling continuous toolpath for each of them. The algorithm then outputs a visualization and a G-code file for the printer. I'll now step through Travel Slicer's algorithm and break it down a little further, beginning with model slicing. Slicing a model is the process of taking the intersection of the model with the XY parallel plane at each layer height, resulting in closed curves, which we refer to as isolated regions. Isolated regions are the area the printer deposits material in at each layer height in order to build up the print piece by piece. Branching models result in multiple isolated regions at a given layer. Once we have all of these isolated regions, we search for a printable ordering of them in outer model travel reduction. And in order to print isolated regions non-linearly, we have to satisfy a few different constraints. The constraints include the following: height dependency. A region can't be printed unless the regions underneath it on the same branch have already been printed. Otherwise, the printer is either printing in midair or it's colliding with the higher regions when attempting to return to lower ones. Nozzle height restriction. Everything within the distance of the nozzle height must be printed before the print head is able to move on to the next section to avoid collisions with the printer armature or the print head. And finally, collision avoidance. Printing a region should not result in a collision with a previously printed part of the model on another branch. To satisfy our first constraint, we construct a height dependency tree in which each isolated region becomes a node. A node's parent is the isolated region immediately underneath it. To satisfy our second constraint, we subdivide our height dependency tree into supernodes, or collections of height-dependent nodes within each nozzle height section, and this allows us to prioritize printing vertical collections of isolated regions, reducing travel movements back and forth between branches. And within each of these nozzle height sections, we verify that no collection of isolated regions overlaps both above and below any other node, and if they do, we split them into a different node and eliminate the possibility of collision. Once we have our set of collected nodes, we search for a printable ordering of them. We construct a weighted directed graph. The nodes of the graph correspond to the collections of vertical nodes, and the edges correspond to a valid travel path that does not result in a collision between the top of the previous node to the bottom of the next node, where the edge weight is the Euclidean distance between them. We search for the shortest Hamiltonian path within the graph, visiting each node exactly once that does not violate our height dependency constraint or our overlap constraint. And once we find the shortest Hamiltonian path for each nozzle height section, we put them all together, resulting in a non-planar printable ordering of isolated regions for the model. Here's an example of how Cura's layer-by-layer ordering of isolated regions differs from travel slicers. You can see that Cura printed every single layer, whereas travel slicers printing them satisfying each of our constraints. Outer model travel reduction outputs a non-planar printable ordering of isolated regions that can now be passed to inner model travel reduction. And when printing a solid model, isolated regions need to be filled with a toolpath consisting of extrude movements. And in order to eliminate inner model travel movements, we generate a space-filling continuous toolpath for each isolated region. Inner model travel reduction makes use of and expands upon prior work called connected Fermat spirals. This is a single toolpath with the same start and end point, allowing us to control the location of the seam and to eliminate, or nearly eliminate, inner travel movements. In the interest of time, I'll be skipping this part, but you can read more about it in the paper. And after inner model travel reduction, Travel Slicer outputs a visualization of the toolpath and a G-code file that can be given to a 3D printer. We tested our slicer on several different models. This was an early test in which we printed the Stanford Bunny in Cerametal and compared it to the version sliced by Cura. In addition to the Stanford Bunny, we sliced and printed a set of 5 different models chosen to test the robustness of Travel Slicer's algorithm. The models were sliced with both Travel Slicer and Cura and then printed in Cerametal on an EZAO Direct Write 3D printer and in PLA on a Creality Ender 3. I'll go a little bit more in depth into 2 of the examples. We tested Travel Slicer on a solid model with nested geometry in which there was a smaller heart within a larger heart shell. And Travel Slicer's toolpath produced a successful print by reducing the number of travel movements back and forth between the inner heart and the outer shell, whereas Cura's toolpath failed as a result of too many travel movements. In addition to a buildup of excess material between the inner and outer structures, Cura's toolpath also failed to adhere to the previous layer as a result of too many movements back and forth. We also tested Travel Slicer on a branching tree model to test collision avoidance and overlap detection. The resulting print, as seen in the beginning slide, was unviable when sliced with Cura as a result of Cerametal's continuous extrusion, whereas Travel Slicer was able to produce a clean print of the complex model. The quality of the PLA prints was comparable when sliced by Travel Slicer to prints produced by Cura, but in some cases it was better. The seam was neater as a result of fewer movements back and forth between the zigzagging pillars in this version. we compiled the number of outer model, inner model, travel movements, travel length, and print time of travel slicer compared to Curo when slicing these 5 models. And travel slicer significantly reduces the number of outer model travel movements. In the case of the zigzagging pillars in Cerametal, it decreases the number of movements from 275 to 4. Travel length was also reduced by a factor of at least 10, and in some cases, a factor of 100. And print time was reduced for all the models, and in the cases of the gears and the nested hearts, it was reduced by more than half. We had similar results for the prints in PLA for all of these categories as well. In conclusion, Travel Slicer's overall contributions include it enables us to 3D print previously unprintable geometries and continuously extruding materials. It reduces material waste, it decreases print time, and it improves print quality. Thank you.
Awesome. Is this open source?
Yes.
Awesome.
It's available on GitHub, on Hand and Machine's GitHub. I probably should have included a QR code.
You can switch up. Yeah, that's fine.
Hi, Jesse from CMU. Awesome work and super well-explained presentation as well. I'm curious, I know you guys designed this for continuous extrusion materials, but considering the lower print times in general, I'm wondering, is there a reason that I shouldn't just use this to replace my normal slicer for all materials?
I mean, hopefully, potentially you could. It did require a extended nozzle, so it was a slight modification, but we basically purchased one from online that was 30 millimeters in length and approximately 14 millimeters in width. Mm-hmm. And we just installed that on the Creality Ender 3, and we had to increase the temperature by about 225, and that was a really good temperature for heat loss as it went down the nozzle, but otherwise it was it worked just fine with respect to that. Yeah.
Cool, awesome.
Thanks.
Great work.
Any other question? I mean, even if you don't have the long nozzle, maybe you cannot save too much, but you can still apply that for.
You can, yeah, right? You can. It's a much shorter distance, so you're still gonna get travel movements back and forth because it has to print the entire model within those sections. Mm-hmm. But you'll still get a benefit of that distance.
Beautiful, and we can access that online on your
right.
GitHub. Beautiful. Any other question? Right. With that, let's thank.